This is a joint work with Raisa Jamterova. She was my PhD student and then went on to work for the Alan Turing Institute. So the topic of this, the focus of this paper is slightly different from the other papers in this session. And I will start by describing the setup, by explaining what this is all about. So this is a mainly theoretical result in online prediction. So I will explain what this means. Then I will discuss some related results, some history. Then I'll present theorems, and hopefully I will have time to discuss some key ideas of the proofs. So first, the setup. The setup is what I would call online learning with signals. So the learner gets a signal, some side information, and outputs a prediction. Then the true outcome is revealed, and the quality of the prediction is assessed by a loss function. So here is the description of the protocol. So on every step, we get a signal, then we produce a prediction, then we see the true outcome and suffer loss due to discrepancy between prediction and outcome. And we want to perform well with respect to the cumulative loss, which is the sum or the accumulated sum of losses. And in this framework, there are important parameters that need to be specified: the outcome space, what outcomes can happen, what a prediction space is, what predictions we are allowed to make, and the loss function, so how the quality is measured. So this is what I will look into now. So in this paper, the predictions will be distributions on a finite set. So a prediction is a distribution or a point from the simplex. Now, what is the outcome? So you can consider two cases here, a simple case and some generalization. So in a simple case, an outcome is just an element of this finite set. And then the loss is the negative logarithm of the probability we assigned to that element. So you can think of the problem as the online classification assessed by logarithmic likelihood. And in a slightly more general setup, you can think that an outcome is a distribution too. And then the loss is the Kullback-Leibler divergence between these two distributions. Well, there was a question from one of the reviewers of this paper to explain, to give some example of a real situation where Kullback-Leibler divergence will be important. Well, I must say our interest here was mainly theoretical, and this is a really straightforward generalization which we did for theoretical reasons. Well, basically because we could. But let me spend a couple of minutes here to show you one example where this really matters. I think this is an interesting example. So suppose that we have a bookmaker that is taking bets on D possible outcomes, and the bookmaker must be paying fair payoffs. Maybe that's a requirement from, from the regulator, or well, unless he makes fair payouts, nobody will bet with him or something like this. So he takes a distribution and pays 1 over Ri for every dollar bet on the outcome I. Well, if I comes true, of course. And there is the gambler. And the gambler hedges the bets and splits the dollar and, well, gets another distribution and splits the dollar as follows between the possible outcomes. And then suppose that the true distribution of the outcome is P. So R is the distribution used for the bets, Q is the distribution for hedging for, so R is the distribution for the payoffs, Q is the distribution for hedging the bet, and P is the true distribution of the outcome. And then you can see that in logarithmic dollars, the gambler's expected gain or the bookmaker's loss can be expressed as follows. So it's the difference of two COLT divergences. The first one is controlled by the bookmaker. The second one is controlled by the gambler. And basically, both the bookmaker and the gambler want to approximate the true unknown distribution of the outcome with respect to the COLT divergence. The bookmaker minimizes what he has to pay, and the gambler maximizes what he gets. So, well, this is an example of a scenario where prediction with respect to COLT divergence makes sense, but I should say that this does not exactly fit our scenario, because in a realistic situation, we would not know the complete expectation. Well, in a realistic situation, just one outcome would happen, and we would not get the full distribution. Still, I hope this provides some intuition. If it does not, well, you can think that we are talking about online classification, and you won't lose that. We're talking about online classification with logarithmic likelihood, and you won't lose that much from this interpretation. Right. So we are going to build an online algorithm for this framework. And the algorithm should perform well in relative terms. So the approach to the theoretical analysis is based on this idea. We want the algorithm to perform as well as the best in a class of competitors. So we won't be assuming any distribution or any law determining the true outcomes. So instead, we want to be as well as any algorithm in a class of competitors in the worst case. And well, so it will be a worst case loss bound. Well, now I will specify this class of competitor we will be looking at. So let the signals be n-dimensional feature vectors. So on each step, we get an n-dimensional feature vector, and we want to work out a distribution on that basis. And a competitor will be a regression type algorithm. So it will have, it's parameterized by theta, which is a vector of n-d coefficients. And the competitor applies, the competitor calculates products of these features and x's, and then makes a distribution out of them with softmax. Basically, it's softmax on top of regression. Well, you can say, well, it's a primitive neuron. It's a primitive neuron, and features are weights in the neuron. So we want an algorithm which will be nearly as well as any of these competitors. It will be as good as a competitor with any value of theta, any assignment of coefficients. So let me show you some background now. So where this all came from. So Raisa and I became interested in this problem when we saw this paper in COLT 2018. It's a paper by Foster et al. And others. Well, in machine learning, there is an online learning there is a specialist with the surname Forster with R in it. So this is a different, it's not a typo, it's just a different person. It's not that Forster. And they built an algorithm with the following loss bound. So the loss of the cumulative loss of the algorithm is less than or equal to and the loss of any competitor plus this extra term. So this term is often called regret. Basically, I will use the word regret to mean this term. You can see that asymptotically in time, the behavior of regret is like this. So it's 5 nd times logarithm of time. So n is let me remind you, n is the dimension of the signal, d is the number of components in our distributions, in our distribution, or number of possible classifications. So the construction in the paper looked to me as rather ad hoc, and I thought that this result could be improved. So Raisa and I produced an algorithm with the following loss bound. So asymptotics used to be 5 nd logarithm of time, and we got 0.5 nd logarithm of time for the same situation. But clearly, there is a question of, of whether this can be improved further, at least asymptotically in time. So we are mainly interested here in the asymptotic over time. Well, one can reasonably ask a question of asymptotics over n. That's also an interesting problem, but this is not what we are looking into. So we are looking in asymptotical behavior over time. Interestingly, if we consider a class of competitors which are logistic regressions, then we can get the regret of 1/2 n times d minus 1 logarithm of time. And n d minus 1 here is the dimension of the parameter for the logistic regression. So for the softmax algorithms, the dimension is nd. Well, fine, but the effective dimension is really nd minus 1. Well, the effective dimension in some loose sense, well, clearly we don't have really nd. We don't have flexibility of nd. Of our flexibility is nd minus 1. So we naturally came up with the question of whether we can reduce our coefficient to 1/2 nd minus 1, and whether this would be optimal. So this is the question this paper answers. So we can get 1/2 nd minus 1, and we can show that this is actually an optimal asymptotics in time. So this is what I will explain. Now some other related work. Well, the main inspiration really for this paper was the 2001 paper by Vovk, where a predictor was built. Well, it comes under the name Aggregating Algorithm Regression or Vovk-Azzuri-Wormuth predictor. It was independently built by Azzuri and Wormuth. And the paper by Vovk produces matching upper and lower bounds on the loss. So we can show them, we can get an upper bound on the loss and show that it cannot be improved. But that's for the case of linear regression on the square loss. So that's a bit different framework, but I should say that we are very much indebted to that paper in terms of inspiration and methods too. Another related paper which I would like to mention is a NIPS paper by Kakadeng from 2005. And it deals with logarithmic loss. It's very close to the setup of this paper, but it's one-dimensional too. And it deals with linear models. It builds an algorithm competitive with any generalized linear model, which is basically some function f applied on top of regression. So distribution produced from regression. And also I'd like to mention a paper by Zhdanov and Vovk, which considers, from 2010, which considers sigmoid applied on top of regression, also one-dimensional. Right, so now I can present the main result, the main theorems. So there are matching upper and lower bounds. So here is the upper bound. Well, sorry, here is the algorithm first. I call it BA because it's really a Bayesian mixture. And A is a parameter. So the algorithm works like this. So we have density function. So on every step, we have density function, which is calculated like this. And basically, it's the it's the normalized exponent of minus loss. So it's density over parameter over features over parameters, and we start from the prior density, which is Gaussian, and A here is a parameter which we are free to choose. Well, I should say that it's positive. And then the prediction that we output Xi is the competitor's prediction averaged over this density. Well, there is a question of how to, well, what's the most efficient way to calculate this? So in experiments, we calculated this with Markov chain Monte Carlo. And it's possible to show that Markov chain Monte Carlo converges here, but well, what's more difficult is whether it converges quickly. So I don't know how this convergence works. Really, this is one of the open questions that interests me. But well, at least we have this explicit expression. And so now the upper bound. So the loss of this algorithm can be upper bounded by the loss of any competitor plus this extra term, plus this regret term. So there is some part of it which does not depend on time. And what depends on time can be bounded as follows. So if we assume that signals are bounded like this, then we get asymptotic behavior of n times d minus 1 over 2 logarithm of time, plus something which is constant in time. Well, but depends on n and d, of course. So this is the upper bound, and the lower bound is probabilistic. So I will say a few words about this. And the upper bound and the lower bound says the following. So we have signals of a fixed norm, of a bounded norm, and we have a random process of outcomes such that for every prediction strategy, the expectation of this loss difference is lower bounded by nd minus 1 over 2 by the logarithm of time, well, minus some constant. So asymptotically, we cannot improve. Asymptotically, we cannot improve this. But the best coefficient in front of the logarithm is nd minus 1 over 2, with nd minus 1 being this effective dimension. Right. Now, let me say a few words about the proof techniques, about the proof ideas. First, the upper bound. Well, the first step is basically the step of the general step which appears in the theory of the aggregating algorithm or other Bayesian mixtures. And you know, in the course that I teach, I call this wealth inequality. So it can be shown by induction that the loss of the Bayesian mixture can be upper bounded as follows. So the task of upper bounded this reduces to analysis of this integral. And this is the integral of the exponent of minus this expression. So what can we do with this Q? We will do Taylor decomposition. There is one important misconception here. There is a standard trick in machine learning that any distribution can be approximated by Gaussian around its mode. This is close, but not quite it. So we take the mode, we take the maximum, and we do a Taylor decomposition there up to order 1 with the remainder of the second order. So there is no term of order 1 because this is the maximum. And the Lagrange remainder can be written as follows.
You have 5 minutes remains.
Thank you. Okay, I should be on time. So this is the Hessian. And what we will do is that we will upper bound this Hessian with a constant positive definite h. Then the integral turns into the standard Gaussian density, which can be calculated, where the integral can be calculated. So the analysis of the upper bound reduces to the analysis of this h, and it has structure that can be captured by the Kronecker product. So the Kronecker product has some useful properties that can be utilized here. So basically, this is the upper bound. This is the proof of the upper bound in brief. But I should say that well, this is not really the main contribution of this paper. It improves on some earlier work, but it improves by a little. But what is more interesting, I should say, oh, right, I should mention another trick here briefly. There is this dimensionality reduction, which we can do on top of this Kronecker product to reduce the dimension to get that ND-1. But that's again, not something very complicated. But what I think is more interesting is the lower bound. So so as I said, the lower bound is probabilistic. So why is that? Well, constructing a lower bound is difficult. So it would be a rather difficult statement with quantifiers. So we need to find signals such that for every for our competitors on every step, for every prediction strategy, something happens. This is rather difficult. And we can get rid of we can cut some quantifiers from the statement with probability. Because in probability, there are some techniques which can be applied here. So for example, well, if we are given a variable x, the value of a variable x, and want to predict some other variable y, then the best approximation is the conditional expectation of y given x. So this is this fact is usually, well, it's usually not very obvious from probability textbooks, but well, you can think of this as the best prediction of y. And this allows us to save some quantifiers from the statement. And this is a very well-known quantity that can be manipulated using standard techniques. So it can be shown that if the outcomes have a joint distribution, then the best predictor for yt would be the conditional expectation. Well, this is almost obvious, but well, this can be proven.
Well, 2 minutes remains.
Thank you. Then, so what is the process? So we clearly cannot use the IID process because, well, if it's IID, then it will be the same on every step, and we would get some result linear in time. And this is too good to be true. We can only get logarithm. But we can be conditional IID. So the variables will be categorical, and they will follow the distribution, which in turn follows a Dirichlet distribution. So first, this Dirichlet distribution chooses some pi, and then y's are categorical with this parameter pi. And this is rather intuitive because predicting the next y would amount to estimating these values of p from past observations. And this will improve with time. So the situation will not be IID and will change with time. And it can be shown that the optimal strategy should make these predictions. The optimal on average strategy should make these predictions. And we can work out the expectation of the loss. So the lower bound is, well, the calculation of the lower bound essentially amounts to the calculation of this expectation. And it can be calculated with pretty standard methods, including the Chernoff-Höfting bound. And then we need some upper bound on the infimum, and it can be done with a particular feature, which is the vector of logarithms of probabilities, and we bound the infimum from above, and we get the required lower bound. And so I've been talking about n of 1, and for n greater than 1, we can do a standard trick of generating n distributions independently and then using them interchangeably. So this is how the lower bound in the proof works. And well, this completes my talk. So I have shown you the upper and lower bounds and explained them and gave some explanation of how they are obtained.